Hey everybody, it's Dr. Daniel Bodkin from Proactive Athletic Performance. In this video, I'm going to go over a test report for the advanced isokinetic test for the knee. And this version of the isokinetic test is different than the original that was developed back in the 1970s. When the original test was designed, the machines weren't able to assess eccentrics. And that's actually how we use our muscles the most, especially with the quadriceps for the knee and the external rotators for the shoulder. But there have been a lot of advances in isokinetic dynamometry over the last 20 years, especially with the HUMAC norm isokinetic system. So this test gives us a lot more information about strength and recovery and readiness for sports. Another thing about the advanced test is that we can't use this test until later in the recovery after surgery, like with ACLs, total knee replacements, and rotator cuffs. We do have other test variations that we can use in the early and middle phases of rehab, but for example, we can't use the advanced test until after month 5 for ACLs and total knees. But it's going to pick up on readiness for return to sports better than the traditional isokinetic test can. So on this first page, we have the report for the quadriceps, and let's first look at the torque lines in the graphs. On the left side here, we have the concentric quadriceps, and that means how strong the muscle is when it's shortening. Just think of the lifting up phase on a knee extension machine. The graph is going to plot the amount of torque the patient achieved over the range of motion of the knee. Now the graph on the right side, that's going to show the torque lines for the eccentric quadriceps. And the eccentric mode is the muscle while it's being lengthened. So that would be the lowering portion of the knee extension machine. And this is actually the most important mode because that's how we decelerate our body weight, either when going downstairs or when we land a jump or when we're making a cut or a change of direction in sports. And this is where if our quadriceps is either being shut down or not producing enough force, we're going to kick in our hip muscles and change our landing and cutting movement mechanics. And that's going to put us at a much higher risk of tearing the ACL or injuring other structures. And this is also what's special about the advanced test because the standard isokinetic test isn't going to pick up on this important eccentric mode of contraction. And the thing about isokinetics and how it's different from traditional isotonic resistance like free weights is that with isokinetics, the speed is held constant, but the resistance is allowed to change through the range of motion. So where you're weaker in the range, there's going to be less torque, but where you're stronger in the range, you're going to get more torque. And this is why we see the line start low on the right side of the graph where the athlete's knee is bent, and then it increases and peaks out in the middle of the range of motion around 60 to 70 degrees, and then the line goes down again as the knee continues to straighten. With the quadriceps, this is the typical torque signature of an ascending-descending curve, and that's what we should see. Now, when we have pain or other pathology present, we can see variations in the lines, but for this athlete, this is what our lines are supposed to look like. In both of the graphs, the right leg is the blue line and the left leg is the red line. For this athlete, the injured side is the left, so that's why the red line will be lower. And if we focus first on the left graph, which is the concentric quadriceps, we can visually see that this patient has a pretty big deficit in strength compared to the uninvolved side. The other thing that I notice is the waviness of the red line, and that's called quad stability or force oscillation, and that just means that the muscle is kind of sputtering a bit when it's challenged at its maximum torque output. Now, if you look at the blue line, which is the right leg, it's smooth, so it's not having that same issue. So let's look down at the numbers for the concentric quad. The first row here is telling us the maximum amount of torque that was achieved by the muscle. And the right leg is the uninvolved side, and it put out 214 foot-pounds. And the left side, which is the injured leg, put out 182 foot-pounds. And that gives us a deficit of 15%. And we want these two to be as close to each other as possible, but we do allow for a normal variation of 10%. So he's outside of that normal amount. And getting to less than 10% asymmetry in all of our strength measures is actually one of the most important measures that we have with the isokinetic test. So we're already seeing a red flag right here in that the patient is above 10% difference between the legs. Now, if we move over to the next column, this is called the coefficient of variance. And that tells us just how closely the 3 test reps matched each other. And we want this to be less than 0.10 or less than 10%. And our athlete hit 0.02 to 0.04, meaning that he only varied 2 to 4% between his reps on the legs. If we see this number above 0.10 to 0.15, then the test reliability is worse because we should be able to have a reliable maximal torque output. So now let's drop down to the next row, and this is called the work per rep. And that looks not just at the peak torque like the row above, but it looks at the strength over the entire range of motion. And this can give you a better look at the overall strength between the two legs. And the athlete here was at 216 for the right uninjured side and 167 for the left injured side. So that gives us a 23% difference in the concentric quadricep strength. And again, we want this to be less than 10%. So we're already picking up on a major red flag for this patient and a high risk of re-injury if he were to go back to his sport at this time. Next, let's go back up to the graphs, and we're going to look at the right side here, which is the eccentric quadricep. The line starts out on the left side of the graph, and that's when the knee is straight. And the line's going to go higher and higher as the quadriceps get stronger when the knee bends again. And we can visually see a deficit in the strength, and it only increases even more as the knee bends. Just like with the concentric graph, we can see the wiggles of the red line, but now they're even more pronounced. And you could even see his muscle quivering while he did the test. And that's just because it hasn't been loaded maximally in isolation, so it doesn't quite remember how to keep a steady force maximally like the right-sided blue line does. Now, even though it's a wavy line, his muscle isn't shutting down completely eccentrically like we can see after a major surgery like an ACL or a total knee. So the red line is wavy because we have that quad instability, but it is showing the correct torque signature. Going down to the numbers, we can see that at peak torque eccentrically, there's only a 9% difference in strength, which is under the 10% difference that we're looking for. But if we go down to the next row, which is the strength over the entire range of motion, there's actually a 15% difference. And the coefficient of variance between the reps was good, just like the concentric side. So next, let's go back to the peak torque numbers, because our next major important number that we pay attention to with return to sports is how strong are the muscles in relationship to the body mass. And if you think about it this way, if your athlete weighs 140 pounds, they need to be able to control up to 140 pounds. But if they weigh 240 pounds, then they need to be able to control 240 pounds. And we have normative values for what the athlete should be able to produce. The concentric quadriceps for males should be able to produce at peak torque 1 foot-pound of torque for every 1 pound of mass. So the ideal number here for a safe return to sports is 100% of the body weight. For females, some research shows that 90% of the body weight is adequate, but we do try to get them as close to 100% body weight as well. And the same goes for larger mass athletes like linemen in American football or centers in basketball. Now, this athlete weighs 230 pounds, and he's able to produce 95% of his body weight with the uninvolved quadriceps, but only 81% of his body weight with the involved quadriceps. So he's close to normal strength for that healthy leg, but about 20% away for that injured side. Going over to the eccentric side, we should be able to produce at least 30% more force eccentrically compared to concentric. So the normative value for the percentage of body weight at peak torque eccentric is 130% of the body weight. And his uninjured side is at 119%, and the injured side is at 108%. So again, we see that small deficit in the healthy leg with a larger deficit in the injured side. The last column we look at for strength is the ratio. And here it's the ratio of the eccentric to concentric. And I like to use the work per rep for this. And we want that to be 130%, meaning that they're 30% stronger eccentrically than they are concentrically. And this is what we refer to as the neurologic balance within the muscle. Our athlete's at 123% for the uninjured side and 135% for the injured side. So he's looking good here for the neurologic balance. So now let's move down to the hamstrings test report. Again, on the left graph, we have the concentric hamstring, and the example here is lifting the weight up toward your butt in a hamstring curl exercise. And we can see that the left red line is significantly weaker than the right, especially in that initial portion of the range. But at least here, both lines are steady and there's no waviness. Looking at the numbers for the peak torque concentric hamstring, the right uninjured side hit 140 foot-pounds and the left injured side hit 98. So that gives him a 30% deficit at his peak torque. But if we drop down a row to the work per rep, which shows the entire range of motion strength, he's at a 15% deficit. And that's because most of his strength deficits occur in that first half of the range of motion where he should be at his peak. If we move to the next column over for the coefficient of variance for the hamstrings, he was good here. And overall for the hamstrings, his reps only varied as much as 5% overall. So it's well within that 10% variability. Next, let's go back to the top and looking at that right side eccentric graph. And on this one, if we start with the right side of the graph, that's with our knee bent. And the graph moves across to the left side, and that shows the strength of the hamstring as the knee is being straightened out. So that would be like returning the weight to the start position of a knee flexion weight machine. And this one really matters because when our athletes strain their hamstrings, it's always as the knee is being straightened out when they're running, so the muscle is being elongated. And looking at the torque lines here, for the hamstrings, we should see that it should be lowest when it's at the right side when the knee is bent, and it should increase all the way to end range. And we see that with the blue line, which is the uninjured side. But with the injured leg, even though it starts out stronger in this mode, as the knee is nearing that end range, we do see the torque dip down. And that tells me that his muscle doesn't like loading maximally near end range. So he might actually be at risk of a hamstring strain as well. So that's another thing for us to consider. Looking at the numbers for the eccentric side, he hit 148 foot-pounds on the uninjured side at peak torque and 124 foot-pounds on the injured side. So he's down about 16% at that important end range portion. If we look at the work per rep, which is the strength over the entire range of motion, here he's actually 2% stronger than the healthy side. And that just represents the fact that he's starting out stronger in the initial portion of the range of motion, but as that injured side hamstring nears end range, it is losing its torque. Next, we're going to look at the strength of the hamstring relative to his body weight. And we want the athlete to be able to hit 60% of their body weight concentrically for the peak torque. And this athlete's at 62% for the uninjured side, but only 44% for the injured side. So he's getting what he should be able to produce on that healthy side, but he is down a bit on that injured side. Eccentrically, he should be 30% stronger than concentric, so he should be able to hit 80% of his body weight. And the uninjured side is at 66%, and the injured side is at 55%. So both sides are down eccentrically for the hamstring. Looking at the neurologic balance of the eccentric to concentric ratio, remember, we want this to be 130%. And the healthy side is at 108%, and the injured side is at 130%. So both hamstrings need to continue getting stronger, with the uninjured side also having the neurologic balance that's out of whack. Lastly, we want to look at the intermuscular balance, and that's the strength between the hamstrings and the quadriceps. Because there's been a lot of research that demonstrates that if we have an imbalance, then that can be a contributing factor to suffering another ACL tear or having a hamstring strain. Now, the hamstring serves as a restraint against anterior shearing that can load and tear the ACL. And we have two different ways at looking at this balance. And the first is the standard strength ratio of how strong the concentric hamstring compares to the concentric quadriceps. And we want this ratio to be between 0.6 to 0.8 or 60 to 80%. So our athlete's involved side hamstring to quadriceps ratio is 0.65 and the uninvolved side is 0.6. So he's actually good for the balance when it comes to the hamstrings protecting the ACL. Now we can also look at what's called the functional ratio, and this is the eccentric hamstring compared to the concentric quad. And we want these muscles to be equal strength at 1.0 or 100%. In the example that I like to use, the concentric quad is like the engine of your car, and the eccentric hamstrings are the brakes. If your brakes aren't strong enough to control the motor, then injury can happen. So for our athlete, he's at 0.85 for the involved side. And we saw that his eccentric hamstring was shutting down at end range of the graph, so this is being reflected in the ratio. For the uninvolved side, his balance is at 0.64, and this is just due to that pure weakness of the uninvolved eccentric hamstring. And we picked up on this when we looked at the neurologic balance earlier. So what's the take home for this test? His surgical side quad is weak compared to both the uninvolved side and relative to his body weight, and the torque output is unsteady with the wavy line. So that right there is a major red flag. For the hamstring, he is weak in the concentric involved hamstrings compared bilaterally and compared to body weight. But eccentrically, both muscles are weak or shutting down at end range. And that's going to put him at a higher risk of suffering another major injury to the knee or having a hamstring tear. So for this athlete, I do not recommend he returns to sports at this point. And the main limiting factor is just the weakness of that surgical side quadriceps, with it being down about 20% compared to the other side and the body weight. His hamstring is down about 30%. Now, most athletes can gain between 15 to 25% of strength every month if they're on a good, solid strength and conditioning program. So if this athlete pushes himself appropriately for the next 6 weeks, he should be at or close to meeting those minimum standards. So that's how we break down the test report and the different things that we're analyzing when we're looking at the advanced isokinetic test after an injury when we're trying to assess if an athlete is safe to return to their sport. Thank you very much.